The sun burns at 15 million degrees at its core. Our galaxy alone contains over 100 billion stars. Beyond it, 2 trillion more galaxies blaze in every direction. And yet, if you stepped out of your spacecraft unprotected, between those stars, you would not burn. You would freeze almost instantly. How can a universe so unimaginably full of fire be, on average, colder than anything we can build on Earth? The answer threads through 350 years of physics. A forgotten conversation between a Swiss philosopher and an English astronomer, and a whisper of ancient light that still bathes every cubic inch of the cosmos at minus 454 degrees Fahrenheit. By the end, you'll understand why the darkness between stars isn't just cold. It's a measurement of the age of the universe itself. In July 1969, Buzz Aldrin stepped onto the surface of the moon. His suit was engineered to survive a staggering temperature swing. The sunlit lunar surface reaches around 250 degrees Fahrenheit. The shadowed side plunges to minus 208. Same moon, same sun, one body, one step, 2 different worlds. The lesson was already there, written in the regolith. In space, heat is not where you are. Heat is what touches you. On Earth, we have a deep intuition about temperature. Step outside on a summer day and the air wraps around you, carrying warmth into your skin. Step into a freezer and cold air pulls heat away. But that intuition depends entirely on something we almost never think about: the air itself. Trillions upon trillions of molecules, colliding with your body millions of times a second, trading energy in every collision. Remove the air, and you remove the conversation. This is the first piece of the puzzle. The vacuum of space contains, on average, just a few hydrogen atoms per cubic centimeter, compared to roughly 25 quintillion molecules in the same volume of air at sea level. According to NASA, in the deep intergalactic void, that number drops to less than 1 atom per cubic meter. There is almost nothing there to carry heat. So when engineers design spacecraft, they face a strange reversal of our everyday problem. On Earth, you worry about things losing heat to the air. In orbit, a spacecraft's sunlit side can climb past 250 degrees Fahrenheit, while its shadowed side falls to minus 250, because there's no air to smooth the difference. NASA's thermal engineers don't fight the cold of space so much as they fight the imbalance of space. But this only sharpens the paradox. If space is so empty, why is it cold at all? A true perfect vacuum shouldn't have a temperature. Temperature in physics is a property of matter, the jiggling of atoms and molecules. No atoms, no temperature. So, what are we measuring when we say the background of the universe is minus 454 degrees Fahrenheit? To answer that, we have to follow a question first asked in the 1800s. A question so simple it sounds like a child's riddle, and so deep it took the invention of modern cosmology to solve. In 1823, the German astronomer Heinrich Wilhelm Olbers posed a puzzle that had quietly haunted astronomers for centuries. If the universe is infinite and filled uniformly with stars, then in every direction you look, your line of sight should eventually land on the surface of a star. Every point in the sky should be as bright as the sun. The night sky should not be dark. It should be blinding. This is Olbers Paradox, and it matters for our question, because a sky full of stars isn't just a sky full of light, it's a sky full of heat. If every direction radiated like the surface of a star, space wouldn't be cold. It would be an oven at 10,000 degrees. The fact that the night sky is dark and space is cold tells us something profound about the universe itself. The resolution came in the 20th century when Edwin Hubble, observing from Mount Wilson in 1929, confirmed that distant galaxies are flying away from us. The universe is expanding, and it had a beginning. roughly 13.8 billion years ago, according to measurements from the European Space Agency's Planck mission. That single fact unravels Olbers' paradox. Because the universe is only 13.8 billion years old, light from stars beyond a certain distance simply hasn't reached us yet. There are galaxies out there whose light is still on its way. Our sky isn't filled with starlight not because stars are rare, but because time is finite and the cosmos is young. And here's the deeper twist. Even the light that does reach us has been stretched by the expansion of space itself. A photon emitted as visible light 10 billion years ago arrives now as infrared, or even microwave radiation, invisible and far less energetic. This is cosmic redshift. The expansion of the universe doesn't just spread galaxies apart, it cools the very light that travels between them, which brings us to the most remarkable thermometer ever built. In 1965, Bell Labs engineers Arno Penzias and Robert Wilson, trying to calibrate a radio antenna in New Jersey, found a persistent hiss coming from every direction in the sky. They couldn't remove it. It wasn't their equipment. It wasn't pigeons nesting in the horn, as they briefly suspected. It was the afterglow of the Big Bang itself, the cosmic microwave background. According to NASA and the ESA Planck results, this ancient light fills every cubic centimeter of space, and it has a temperature, 2.725 Kelvin. That is minus 454.76 degrees Fahrenheit. This is what people mean when they say the temperature of space. It's not the temperature of nothing. It's the temperature of the universe's first light, stretched and cooled by 13.8 billion years of cosmic expansion. When the universe was 380,000 years old, that same light was at roughly 3,000 Kelvin, a glowing orange, like the surface of a cool star. The entire cosmos was bathed in warm light. If you had lived then, space would not have been cold. It would have been warm in every direction. But as space expanded, the wavelengths stretched. Orange became red, red became infrared, infrared became microwave. And the temperature dropped by a factor of 1,000. So the cold of space is, in a very real sense, a consequence of time. The universe is cold because it is old and vast and still growing. Every second that passes, space expands a little more, and that ancient light stretches a little further, and the background temperature drops another imperceptible fraction of a degree. This is why an astronaut near Earth doesn't freeze instantly. The sun is close enough to pour radiation directly onto their suit. Heat in space travels almost entirely by radiation, not conduction. If you're in sunlight, you're cooking. Step into a shadow, and the only warmth reaching you is that faint 2.7 Kelvin whisper of the Big Bang, which is to say, almost none at all. Step back, and a stranger picture emerges. The universe contains unimaginable heat, stars, quasars, black hole accretion disks reaching millions of degrees, supernovae briefly outshining entire galaxies. And yet, average it all out across the volume of the cosmos, and the result is stunningly close to absolute zero. The fire exists. It just has nowhere to go. This is the second great insight. A star's heat isn't contained. It radiates outward in a sphere, and the surface of that sphere grows as the square of the distance. By the time the sun's light reaches Pluto, it is 1/1600th as intense as it was on Earth. By the time it reaches the nearest star system, it's functionally gone, diluted into the cosmic background. Heat in the vacuum is a fountain pouring into an ocean, and it will only grow worse. Cosmologists studying dark energy, including teams publishing in Nature and the Astrophysical Journal, project that the expansion of the universe is accelerating. In the deep future, hundreds of billions of years from now, galaxies beyond our local group will recede so quickly their light will never reach us. The cosmic microwave background itself will redshift into undetectability. The universe will grow darker and colder. This is sometimes called the Big Freeze, or heat death. Not because the universe will become suddenly icy, but because it will run out of temperature differences. Stars will burn out. Black holes will slowly evaporate over timescales so long they make our current universe look like a single heartbeat. And eventually, everything will settle toward the same near-zero temperature, with no energy left to do anything at all. It reframes our own planet. Earth is not a typical place. Earth is a rare, improbable pocket of warmth, held together by an atmosphere that refuses to let the heat escape. We are a campfire in a cathedral. And the cathedral, for reasons written into the geometry of space-time itself, is almost entirely, breathtakingly cold. So when we ask why space is cold, the real answer isn't about vacuum or distance or even stars. It's about time. The universe is cold because it had a beginning and because it's expanding, and because light, no matter how bright, eventually runs out of places to go. The darkness between stars is the shape of cosmic history itself. Every time you look up at the night sky, you are seeing Olbers Paradox resolved. The darkness above you is not empty. It's the signature of a finite, expanding, ancient cosmos, still cooling from its own birth. The cold of space is a memory, and we, warm, small, thinking briefly beneath it, are the strangest thing in it. If you want to keep exploring the quiet strangeness of the cosmos, subscribe to Cosmic Edge.